Hello, Dr. Swandi Shamano here. Welcome to Punch's Chemistry, where we punch chemistry in the face. Today, we'll look at chemical bonding. Chemical bonding is the chemical combination of two or more atoms to form a molecule or a compound. Atoms combine chemically to achieve a complete valence shell of electrons. In general, atoms can do so in three ways. 1. By losing of electrons, which is done by metal atoms. 2. By gain of electrons, which is done by non-metal atoms. Or by sharing of electrons, which is done by two or more non-metals. The electrons in the last shell of an atom are called valence electrons. There are basically three types of chemical bonding. Ionic bonding, which involves a metal losing electrons to a non-metal. Covalent bonding, which involves two non-metals sharing electrons together. Metallic bonding, which occurs within the structure of a metal. Let us look at ionic bonding. Ionic bonding is a type of bonding which involves the transfer of electrons from a metal to a non-metal. It takes place between oppositely charged ions. The ions are arranged in an ionic lattice and are held together by electrostatic forces of attraction. Let's look at an example. Here, sodium, which is a metal, reacts with chlorine, a non-metal, to form a compound called sodium chloride. Formula NaCl. Remember, the valency for sodium is 1 and chlorine, the valency is 1. So in the formula, there are no numbers, there are no subscripts. So we'll draw the structure of an atom of sodium. Remember, the atomic number for sodium is 11, meaning it has 11 electrons. So the configuration will be 2, 8, 1. 2 electrons in the first shell, 8 electrons in the second shell, and 1 electron in the outermost shell. Let us also draw the electronic structure of an atom of chlorine. So chlorine, the atomic number is 17. So the configuration will be 2, 8, 7. 2 electrons in the first shell, 8 electrons in the second shell, and 7 electrons in the outer shell. The sodium atom will lose an electron, which will be transferred to the chlorine atom. So we'll discover that the sodium atom will now have the outermost shell with 8 electrons, meaning it is stable and forms a sodium ion with a charge of plus. The chlorine atom, on the other hand, having gained an electron from the sodium atom, will have also a filled outermost shell which will have 8 electrons. And in this case, the chlorine atom has become a chloride ion with a charge of -1. So this is how we represent the structure of sodium chloride. Let us look at another example. Here, magnesium metal reacts with chlorine to form magnesium chloride. In this case, the valency of magnesium is 2 and the valency of chlorine is 1. The 2, which was for magnesium, becomes the subscript for chlorine. Therefore, the formula becomes MgCl2. This, in essence, tells us that one magnesium atom will react with 2 chlorine atoms. Because the magnesium atom will lose 2 electrons, 2 chlorine atoms will be needed, as each chlorine atom takes 1 electron. Let's see how we represent this by way of structures. Magnesium has atomic number of 12 electrons. Configuration 2, 8, 2. 2 electrons in the first shell, 8 electrons in the second shell, and 2 electrons in the outermost shell. So it's these 2 electrons in the outermost shell that will be lost. Let's draw a structure for a chlorine atom. Configuration for chlorine 2, 8, 7. 2 electrons in the first shell, 8 electrons in the second shell, and 7 electrons in the outer shell. So like we said, we have 2 atoms for chlorine. The magnesium atom would then lose its outer electrons, with each electron going to 1 chlorine atom. In that case, the magnesium atom becomes a magnesium ion with 2+ charge. The chlorine atoms, on the other hand, will become chloride ions with a charge of -1. So that's how we show the structure of the compound of magnesium chloride in ionic bonding. Let's take a look at the properties of ionic compounds. Ionic compounds are made up of ions, metal ions and non-metal ions. Ionic compounds are solids at room temperature and pressure. They are non-volatile, meaning they don't easily evaporate. This is because they have a high melting and high boiling points. And the high melting and high boiling points is due to the strong attraction forces between the ions. Ionic compounds are water soluble, but insoluble in organic solvents such as paraffin or petrol. Ionic compounds are able to conduct electricity when molten or in aqueous solution, but not when in solid state. This is because when in aqueous or molten states, the ions are free to move about and hence can conduct electricity. Let us now look at covalent bonding. Covalent bonding is a type of bonding that occurs between nonmetal atoms, and it involves the sharing of electrons. In order to obtain a full outermost energy shell, the atoms tend to share the electrons of their outermost shells. This leads to the formation of molecules, molecular elements if the atoms are of the same element, or molecular compounds when different atoms from different nonmetals combine. In a single covalent bond, 2 electrons are shared, 1 from either atom. In a double covalent bond, 4 electrons are shared, 2 from each contributing atom. Let's look at some examples. Water, H2O, is an example of a covalent compound. There's 1 atom of oxygen and 2 atoms of hydrogen, and then the sharing of electrons. We also look at methane, CH4, where there is 1 carbon atom and 4 hydrogen atoms. And also look at carbon dioxide, CO2, 1 carbon atom and 2 oxygen atoms. Let us demonstrate how the bonds are formed. So these are called dot and cross diagrams because the electrons are represented by dots and crosses. For water, we'll start with oxygen. We'll use crosses for the electrons of oxygen and dots for the electrons of hydrogen. We'll draw the structure for oxygen. The configuration is 2, 6. 2 electrons in the first shell, 6 electrons in the outermost shell. So we'll draw first of all the first shell. We'll show the 2 electrons. So before we show the 6 electrons in the outermost shell, let's first of all include the hydrogen so that we isolate the electrons which are being used for bonding. So the hydrogen atom will contribute 1 electron and the oxygen atom also contribute 1 electron. Remember, for a single bond, we said 2 electrons are shared. Or in short, there is a pair of electrons involved in a single bond. So I have 1 hydrogen atom here, and the other hydrogen atom on the other side also contribute 1 electron, with oxygen also contributing 1 electron. We can now include the remaining electrons for oxygen. Since we've already used 2, it means we have 4 left. So the electrons should be paired. We'll do the same for a molecule of methane, CH4. So we'll draw the structure of carbon atom, configuration 2, 4. 2 electrons in the first shell. The 4 electrons in the outer shell. First we'll deal with the electrons being used in the bond. 1 hydrogen brings 1 electron. Carbon brings 1 electron. Another hydrogen comes along, brings 1 electron, and so does the carbon, and another, and another. So in total we have 4 hydrogen atoms. And this shows that we've used 4 electrons from the outer shell of carbon, meaning we've used all the electrons. And if we count the total electrons now, for carbon there are 8, meaning carbon is stable. Let us now look at carbon dioxide. 1 carbon atom, 2 oxygen atoms. So here, we discover that carbon and oxygen will form what is called a double bond, meaning 4 electrons will be involved. 2 electrons from the oxygen atom and 2 electrons from the carbon atom. The bond will have 4 electrons in total. Another oxygen atom will come along, contribute 2 electrons, and the carbon will again contribute 2 electrons. So the carbon has already used up all the 4 electrons in the outer shell, and therefore won't draw any more electrons. And if we count the total number of electrons in the outer shell for carbon, we'll find that there are 8 electrons. meaning it is stable. For the oxygen atoms, we've used 2 electrons, so we're left with 4. We'll include those 4 electrons in the outer shell. Counting the total number of electrons, it shows that even the oxygen atoms have 8 electrons in the outer shell each, meaning they are also stable. We now look at the properties of covalent compounds. Covalent compounds have low melting and boiling points. This is because of weak forces of attraction between the molecules. Most covalent compounds are gases or liquids at room temperature and pressure, except for some giant structures which are solids at room temperature and pressure. Covalent compounds do not conduct electricity except graphite. They are insoluble in water but soluble in organic solvents. They are made up of molecules. So we can generally see that the properties of covalent compounds are pretty much the opposite of the properties of ionic compounds. Let us switch gears a bit and look at giant molecular structures. So these are still covalent compounds. Covalent substances with giant molecular structures consist of an extensive network of atoms held together by covalent bonds. Substances with giant molecular structures have high melting and boiling points, as a lot of energy is required to overcome the strong covalent bonds between the atoms. Examples of 2 such giant structures are diamond and graphite. Diamond and graphite are allotropes of carbon, which have giant molecular structures. The carbon atoms in these structures are arranged in different manners. This accounts for the different properties of diamond and graphite. So below are the structures of diamond and graphite. So we can see the differences in the structures, the differences in the bonding. We see that diamond, each carbon atom is bonded to 4 other atoms. And for graphite, each carbon atom is bonded to 3 other carbon atoms. See that. Each carbon atom in diamond is covalently bonded to 4 other atoms. All the valence electrons in each carbon atom are used. Therefore, diamond cannot conduct electricity. For graphite, on the other hand, each atom is covalently bonded to 3 other atoms. This leaves 1 electron free, and this electron will be able to move about and conduct electricity. Let's now jump to metallic bonding. So in metallic bonding, we're talking about the bonding within the structure of a metal. It's within the same metal. So this bonding occurs between the positively charged ions, the nucleus, and the electrons, the free electrons. The electrostatic force of attraction between the positive ions and the mobile electrons hold the structure together. The delocalized electrons are free to move about within the structure of the metal and conduct electricity. Metallic bonding also accounts for other properties of metals such as malleability, ductility, high melting points, and luster. This wraps up today's lesson, but before you go, take a look at some review questions.